So at 5.33 feet, we have 8,533 pound-foot bending, okay? What you'd want to do is take at least one other point on each side, okay? To help draw it up, just to give you a more accurate estimation, okay? Before we do that, does everybody follow what happened here?
Why was it negative 600 times 5.33? Why do we decide that was negative?
Because you're using that
Because
5.3.
We're looking at how is this causing rotation about the point 5.33 feet away from R1, okay? So we said that R1, when we grab on, is rotating it this way. Our point load from our uniformly distributed force when we grab on here is actually rotating it this way.
So,
Because remember, the force is acting down, and so it's going to try and rotate like this.
Okay.
Counterclockwise rotation, so we use a negative value.
3,200 times 5.33 right here. You have 17,171.
Yep.
I have like 120 less than that. You just guessed that one, or?
3,200 times 5.33. Yeah, 17,056.
Okay.
So that gives us what actually?
8517.
85 what?
17.
17?
Yeah.
There we go.
And that, so that gives us the height of the, like the apex of the curve.
The apex of the curve on the bending moment diagram. Okay. It also tells us.
And it's 5.33. That apex is 5.33 in.
Yep.
All right.
Right? That's what this is telling us. Okay? And the reason I determined at that value, I'm not just using it arbitrarily. Remember that we determined that that is where our shear equals 0 in the shear diagram. Okay? So let's look at the moment when x equals 2. So we're 2 feet away. Okay? So what do we have?
R1 times 2.
Times 2 feet, right?
Yeah.
And that's still going to be causing positive rotation, right? What is our uniformly distributed load doing?
Going negative.
It's going to be negative again, right?
Mm-hmm.
Where is it located?
At 2 feet.
Careful.
No,
1 foot.
1 foot.
It's going to be 1 foot away, right?
It's be in the middle.
So remember, what do we need to do with our uniformly distributed loads for analysis? Turn them into a point load, and if they're acting over that entire distance, put them at the midpoint. Okay?
So just stay at, so it'd be 12.
So we have 6,400 pound-feet minus 1,200 pound-feet. Right?
So it'd be 52 at 1 foot.
It would be 5,200 pound-feet at 1 foot
At 1 foot.
from R1. Or sorry, I'm sorry, 2 feet from R1.
Oh yeah.
let's look at, see, so we got 12 feet there. Let's look at M of x equal 9. Okay, so now we're about here. What do we have? Still have R1, right? Times 9 feet.
Negative 600 times 9 is 4.5.
Careful, what do we have to do first? I agree with you that 4.5 is your distance, right?
9.
But we have to multiply this by 9 feet to get it into a magnitude?
Then it's gonna
Okay. So 27,000 and 1,800, so 28,800 pound-feet. Minus 4.5 times 5,400.
not the right answer.
4,500?
Okay, 4,500 pound-feet. So, this is 16 feet, so we're about here.
We know where it crosses.
Yeah. What's happening at this reaction?
Zero.
At x equals 12. Is it all right
Was.
if I remove x equals 0 and x equals 5.33?
Yep.
So we'll still have R1 times the 12 feet, right? What else are you going to have? Careful. We're 12 feet away, right?
So it's
And
right through.
R2 is passing through that point. So what's the distance of R2?
Zero.
It's going to be 0, right? So it's not going to have any rotational impact.
Okay.
You're right, though, in that we have to take it into account in our shear, right? We don't have to worry about it at this point with regard to bending, because it's not trying to bend the beam at all at this point. Okay? Do we, though, have to take into account our uniformly distributed load?
Yes.
We still have to take that one into account, right?
600 times
Okay.
12
Okay?
So that's where I must have gotten that 4,800.
That, yeah, that could be. That could be too. Just transcribed everything incorrectly. Okay, so at 12 feet, now we're down here, so half that. Okay, and then what about x equals 16? What are we going to have? So now we're all the way out here.
That goes back to zero.
Hopefully, right? If we have rotation, out here, we're gonna have some issues.
There's no R2.
What is R2 trying to do when we're way out here?
Bend.
In what direction? Is it trying to rotate this way?
Positive.
It's trying to do positive, right? Right? And we're 4 feet away?
Okay.
Okay? So remember, we're looking at these, we're marching along the beam. Okay? And we really should determine one other point between here and here to see, does this look like this, or does it look like that? Okay? Times 2 foot. Okay? 32,000 and... And 12,800. 200 times 14. So it's 57.6, so it's minus
1,200.
1,200.
Yeah. So what we'll find is that we actually have a curve that looks something like this, okay? And draw everything together. Okay?
Yeah. Yeah, that's why we did the 14.
What was the question, Terry?
So you want to make it like actually rounded in this graph?
Yeah, I mean, ultimately speaking, if we determine what our maximum is, we know what our capacity needs to be, right?
Right.
Although that looks like I'm taking our capacity out. Too far? Something goofy like that, okay? One other last one. Where did my sheet go? There. Okay. One last, and we'll have just enough time to look at it, is a cantilever beam. So this beam has a cantilevered section, right? In case we aren't aware of what a cantilever is, it's any sort of beam where we're extended out a distance and it doesn't have a support at that other end, okay?
I do now.
I'm happy about this.
Think about what that means from a shear standpoint. What's our shear diagram going to look like? Are we going to have anywhere where it's going to be crossing zero?
Probably, yeah.
Yeah. Well, it depends on what's going on in the rest of the beam, but
Okay. Do we have, so if we have a beam,
because it would go right back through the reaction and then hang out the end, wouldn't it?
and I put a force out here, and I anchor it into the wall, where are my reactions?
The wall.
At the wall, right? So are there any other forces acting in the opposite direction along the length of this
So there
beam?
is going to be no shear at zero.
Right.
Because you can't have shear going through that hole.
Yep. Okay, so let's look at the case where
Make new diagrams.
we have our beam running from left to right. We're going to anchor into our wall. We're actually going to put on a uniformly distributed load.
These are flats, which are weird. Deer in the middle of it.
It's going to be 500 pounds per
Great.
foot.
Let's do it.
And this is going to be 10 foot.
Fantastic.
Okay? What's our F sub y?
What?
Our forces in the y direction.
500 pounds per foot.
Times?
So 5,000.
10?
Times 10
Well,
foot.
oh, we're going from, okay, the right side.
Well, we only have one reaction, right?
Yeah.
Our reaction's only located here. Okay, we've got 10 minutes, so we gotta go fast, right?
Yeah. Well, we can stop right there.
No, we can't stop right here. If we stop right here, then we can't start on chapter 4 on Tuesday.
Can't stop, won't stop.
Trust me, you wanna start on chapter 4 on Tuesday, right? You don't wanna be doing this anymore, do you?
No, but
Okay.
I don't want to know more homework.
But we're gonna have a reaction here, right? In the wall. It's gonna have a Y component.
It's not here, there's no homework. I know. I don't really know.
Okay, so we know that this reaction has to take all this load of this beam, right? What happens if it doesn't? If the reaction at the wall can't support that entire load, what does this beam do?
Break.
Falls.
Cheers.
It's either gonna shear off, or it's gonna bend off and snap, right? It's gonna fail in one of those two ways. Okay, so it has to have that capacity at the wall, okay? But now let's look, what does our shear look like?
5,000. Oh, the diagram?
Yep,
It's gonna be a uniform, well, it's gonna be just like a,
it's gonna be dropping down
Straight
constant
drop.
slope, right?
yeah,
Okay.
at 500.
So let's start
Pounds per foot.
right at the left edge of our beam, okay?
Wait, can,
How much shear?
once you,
You start at 0 on the left side and go up to 5,000?
No,
Yep.
well, why
What?
would you go up?
Because your 5,000 is over there at the
Well,
wall,
I-
the reaction.
Okay, and Marshall brings up a good point. Why would you go up? Here, truly, we've defined this as being 0, right?
Yeah,
So our shear should be traveling in the negative direction, right?
yes.
Oh, really? Oh, yeah, right.
why?
If we, Terry, if we started here,
Mm-hmm.
we would start at 5,000 and
Yep.
go down to
Yep.
0, okay? Because here, what's your shear, Rush?
0,
0, right? If you go 1 foot away, what is it?
negative 500 pounds.
Negative 500 pounds, right?
Oh,
Just because we
okay.
defined that as
Once you're
yeah.
over the wall.
So
it should
as
back
you go,
up to 0.
okay, I got you.
Okay, so here it's 0 pounds,
5,000.
here it's 5,000 pounds. Now we've defined it as negative 5,000 pounds because how we've defined our direction and how we're analyzing. Does the beam care that it's negative 5,000?
No.
All the beam cares about is that it's 5,000, right? It just cares about in here. As long as our capacity can support 5,000 pounds, beam doesn't care which side we're analyzing from. Okay? Does that make sense to everyone?
Yeah.
All right. What do you think the moment diagram will look like then? So now we're looking at bending.
How did those ones go? Is that what we just did?
So we just do
Okay.
so
Right, the loop one?
yeah.
No. Would it just be like,
What about here?
it touched the beam? 0.
It's going to be 0, right?
It just, it wouldn't connect back up though, would it? It would just be like a,
Probably just occurred.
yeah,
What about, let's go 2 feet away.
1,000.
Careful. What do we need to do with our moments?
Negative 1,000.
We have to.
Times 1, still be 1,000.
Yep. Okay, so here we're down to minus 1,000 pounds per feet. Let's look at 6. So if now we're going 6 feet away. do we have?
500 times 3,000. Then times what? 3, so 9,000. Like that don't make sense.
Yep.
No.
Right, because we take the magnitude, 5,000 times that 6 feet, drop it at that midway point. It's going to be 3 feet away. Okay? And then let's look at m of x equals 10. Yep.
So it can go beyond your shear, obviously.
Can go beyond your shear.
You get 25,000 pounds of the shear's 5,000.
Yeah.
Okay.
Yeah, that's always available to you for bending. And hopefully that makes sense to us, right? If we think about this beam, where we have a uniformly distributed load, as we're getting closer, this beam is trying to, because it has more load being exerted on it, it's going to try to bend, going to try and have more bending moment about it, right? Picking up more load as you're getting closer to the reaction.
So MX10 doesn't mean that the weight's right at the wall.
It's right before.
It's right before.
Not for the bending.
So is that saying it can hold more power? 25,000 pounds? And what the hell is that saying?
No, what it's saying is the total exertion of all the force on the beam at that point is trying to bend it with a force of 25,000 pounds per foot. Okay?
Okay.
Does that mean you have to have a beam that'll hold 25,000 pounds?
Yep.
But it just seems
Rather than a
like,
beam that holds 5,000 pounds?
Well, it has to have both, right? It has to be a beam
if you want to bend more,
that has a shear capacity of 5,000
Yeah,
pounds
so it has to be.
and a bending capacity
Because it's.
of 25,000 pounds per
One
foot.
reaction holding
Two
it.
different qualifications.
It's two different portions of
Right here,
analysis.
it's gonna
Yep.
take 25,000 pounds.
that's what I'm saying, is it the strength.
Yeah, and out here, it's only gonna take 5,000.
So it takes 25,000 pounds to bend right at the wall.
It only
Yeah.
takes 10 to bend at the
And
end.
only,
Yeah.
that's what,
It's 1,000.
that's what the hell I've been saying.
Yep.
So like if you have your arm out, you have a dumbbell?
Yeah. You speaking my language there?
I don't know, what do you
Gumming
use,
it
like
up for me?
kettlebell?
A dumbbell.
Kettlebell.
Okay? So, ready to try some of these for homework as well?
Are you kidding?
You know, we say we're always ready.
Yeah, we're ready.
You ready to push back another assignment?
Didn't I try it?
If we need to.
Ready.
I'd rather have you understand what's going on than try and keep powering forward.
You know what really sucks about these questions? Like when you look through the book, like I
Yep.
was trying to look at the, and I went back in the book, it's like impossible to read. It does not go in this nice little progress that you put on the board. It's scattered
Like all of a
through
sudden
like
you're
3 different
here,
pages.
don't you get?
Oh, I see what you're saying, yeah. And I think,
Show work,
I think too,
so
the
like
other,
it
the other
makes
portion
it
with the book is it makes some intuitive leaps. After it's shown
Yeah.
a certain type of
Yeah, it
problem
doesn't
a few
repeat
ways.
itself or-
Yep.
The
Yep.
book's just hard to read. I don't, and we found 2 or 3 mistakes now, so we should just burn them.
I will be honest, I don't know that I'm gonna teach with this book again. I like the setup of it, but yeah, stylistically, I don't know that it's the best, so. Okay, so I'll post your homework, and actually, Rush, the first portion of the homework is doing the bending moments of the shear diagrams that you're doing this week.
Okay.
Okay, so I'll have that posted. I'll extend the homework that was as currently assigned for 10 a.m. this morning. It'll be 5 p.m. tomorrow. Steve, if you want to resubmit.
I gotta redo the last one.
And if you've submitted through Canvas,